We live in the area of great space exploration. So far, dozens of probes have reached the furthest corners of the solar system. Orbital telescopes are capable of covering practically all of the visible universe, but this is just the start of our journey. There are thousands of stars and planets waiting for their explorers within just a few dozen light years from us. Today, we'll set out on an exciting journey to follow the great missions of the past, present, and future. Our flight will begin dangerously close to this scorching sun, where the Parker probe is doggedly approaching the boundless ocean of turbulent plasma with every orbit. Then we'll cross the solar system and follow the legendary voyages of the probes that have been on an escape trajectory from their native planet several decades by now. After that, we'll take a look at the technologies of the nearest future, which are potentially capable of getting us beyond the solar system. They will help us cover several light years to reach the stellar system closest to ours, Alpha Centauri. Meanwhile, conventional technologies may not be enough to reach more remote stars. That is where the Alcubierre drive steps in, an amazing concept somewhere in between science and fiction. This technology will allow us to carry on with our journey through ice-cold space and visit a few fascinating stars dozens of light years from the Earth. Let's get ready and begin. On the 21st of November 2021, the Parker Solar Probe was just 8.5 million kilometers away from the Sun. It was its closest approach ever to our star. This means that it was also the first probe that got to brush against the Sun's corona. But why was it necessary to go through a number of technical difficulties and approach the Sun that close? What is Parker after? It had to get that near the star to areas where everything around turns into ash. To realize the purpose, we have to see what we already know about our system's star. To begin with, the Sun is a main sequence star whose age is approximately 4.6 billion years. It currently falls into spectral class G2V, which on balance makes it a typical yellow dwarf. The Sun's surface temperature is about 5800 Kelvin, which is 5530 degrees Celsius. But it should be mentioned that there are both colder and hotter areas to be found on it. Incidentally, the star's inner layers and its outer corona are as scorching hot as millions of degrees, but for all that, they barely contribute to the visible radiation. The Sun's average diameter is around 1.4 million kilometers, which is 109 times that of our Earth. As for the star's mass, it reaches 2x10^30 kilograms, or 333,000 times that of the Earth, and actually accounts for 99.9% of the mass of the entire solar system. We're used to seeing the Sun as small, but in fact, it is larger and brighter than 80% of all the stars in our galaxy that we know of. Hydrogen accounts for 92% of the Sun's overall volume. In one of our previous videos on stellar evolution, we mentioned that it is mainly this gas that fuels thermonuclear reactions for the overwhelming majority of stars. When its temperature reaches incredibly high values as they merge, hydrogen nuclei release great amounts of energy and transform into helium, which gradually accumulates in the star's center. At the moment, helium accounts for 7% of the Sun's volume and 25% of its overall mass. In addition to helium, stellar matter contains other elements as well, like carbon, oxygen, nitrogen, and iron, but their percentage is quite negligible. The Sun has an elaborate structure and is made up of several layers that differ in their properties. A massive core is at the center of the star. Estimates show its diameter to measure 25%, the Sun's overall size. The core's temperature measures as much as 14 million Kelvin, while 1 cubic meter of the material weighs around 150 tons. It is here that the thermonuclear reactions, the source of energy for our star's luminosity, run their course. Every second, approximately 4.26 million tons of stellar matter is transformed into luminosity as a result of these processes. The core is surrounded by the so-called radiation zone, which continues to the point of 0.7 the Sun's radius. The density of matter in this area is too great for it to get mixed up thoroughly and thus to carry heat to the upper layers of the star. That is why the way energy is transferred here is this. Particles of stellar plasma are continuously absorbing photons and radiating them again. Mathematical modeling shows that the temperature in this part of the star dramatically changes from 7 million Kelvin in its depth to 2 million Kelvin on the outer boundary. Estimates reveal that a quantum of light produced by the core may stay in the radiation zone from 10,000 to 170,000 years, and only then move the distance between the probe and the surface of our star will shrink to become an all-time short, just 6.5 million kilometers. Estimates show that when the probe is in its perihelion, its solar shield may heat up to 1370 degrees Celsius, which is 3 times hotter than Mercury's sunny side and only slightly lower than the melting point of iron. Even now, the probe is whizzing at a speed of 163 kilometers per second in its perihelion, but it will eventually accelerate to 200 kilometers per second, which will make it the swiftest man-made space object made so far. The probe's life expectancy cannot be that long. On reaching the closest possible point to the Sun, Parker will manage to complete several orbits around it, which is supposed to take roughly a year. All this time, it will keep losing speed, and the scientific instruments on board will be exposed to extreme temperatures and powerful radiation. Eventually, they will all be out of order, and the probe itself will descend into the scorching depths of the Sun to be totally swallowed up by a fathomless ocean of blazing plasma. But before it happens, Parker will beam great amounts of useful data back to the Earth, which will help us make yet another step in space exploration. This is potent proof that Parker's flight will not have been wasted. Spacecraft New Horizons. Start of mission, 19th of January 2006. Distance to Earth, 52 astronomical units. Speed, 14 kilometers per second or 3 astronomical units per year. Main goal, Pluto and Charon. Mission status, successfully completed. Condition, operational. Just like most other interplanetary space probes, New Horizons performed a gravity assist maneuver near Jupiter before setting out to its target. Not only did it greatly boost the spacecraft's speed, but also allowed it to capture high-quality images of the largest planet in the solar system alongside its satellites. Besides, the probe's cameras captured the first video ever of an erupting volcano on the surface of Jupiter's satellite Io. After the gravity boost had been completed, the probe made for the main target, Pluto. The spacecraft reached the planetoid's environs in January 2015. Mission's main goal was to explore Pluto and Charon from different perspectives, which involved taking photos of and mapping these remote space objects' surfaces. In addition, the probe estimated the magnetic field's values and the solar wind activity close to the objects and collected information about their atmospheres and surface reflection properties. It goes without saying that the program also involved the search for Pluto's as yet undetected satellites and more accurate measurements of Pluto's orbit's parameters. Having completed the main mission, the probe continued to be useful. It flew beyond Pluto's orbit and went on to explore objects in the Kuiper belt. That is how images of Quaoar 1 and Arrokoth were produced thanks to the probe's cameras. The distances to the stars Proxima Centauri and Wolf 359 were measured. Unfortunately, the radioisotope generator on board the spacecraft is expected to start running low from 2026, and eventually, all the meters on its way beyond the boundaries of the solar system, and by the year 2038, the distance between the probe and the Sun will have grown to be 100 astronomical units. By that time, the energy generator on board the spacecraft will have stopped operating completely, and it will be impossible to get any connection with it. Following a hyperbolic orbit, New Horizons will exit our system never to come back. The same thing happened with 2 other probes, Pioneer 10 and Pioneer 11. They hit an escaped trajectory from the solar system a while ago. In fact, they were the first automatic space probes ever to be sent into interstellar space by humans. Spacecraft Pioneer 10. Start of mission, 3rd of March 1972. Distance to Earth, 127 astronomical units. Speed, approximately 12 kilometers per second or 2.5 astronomical units per year. Main goal, Jupiter. Mission status, successfully completed. Condition, not operational. The spacecraft reached Jupiter's system on the 4th of December 1973 after completing a 641-day journey through space. During the mission, images of the gas giant's surface and its largest satellites were beamed back to the Earth, and the planet's atmospheric composition and magnetic field were gauged. In addition, Jupiter was found to emit 2.5 times more thermal energy than it receives from the Sun. The data, unique at the time, became the basis for understanding the makeup of gas giants and their satellites. The trajectory of the second probe, Pioneer 11, through space past Jupiter 2, but its main target was the other gas giant of our system, Saturn. The probe's scientific instruments gauged the planet's magnetic field, and the cameras on board took quite a few snapshots, not only of the gas giant itself and its system of rings, but also two of its satellites, Titan and Mimas. According to estimates, the current distance between Pioneer 11 and the center of our system is around 106 astronomical units. On completing their main mission, both probes continued on their way, moving further and further away from the Sun. Unfortunately, both of them are out of range now, with the last signal from Pioneer 10 received back in 2003, and the last signal from Pioneer 11 was received in 1995. Supposedly, both of them are now rapidly moving beyond the boundaries of the solar system. Incidentally, having no chance of ever catching up with either of the two probes we're going to talk about next. Spacecraft Voyager 1. Start of mission, 5th of September 1977. Distance to Earth, 154 astronomical units. Speed, around 17 kilometers per second or 3.6 astronomical units per year. Main goal, Jupiter and Saturn. Mission status, successfully completed. Condition, not fully operational. The contribution of Voyager 1 to the solar system's exploration can hardly be overestimated. It is thanks to this probe that several new Jupiter satellites were discovered alongside its ring system, which was big news. The Voyager's cameras captured volcano eruptions on Io and provided hard evidence that Jupiter's Great Red Spot is an enormous storm. The probe beamed back hundreds of photos of the largest planet of our solar system and its satellites. After the spacecraft crossed Neptune's orbit, the meters on board sent back a great amount of valuable data about interstellar plasma. Voyager 1 left both the Kuiper Belt and the heliopause behind a long while ago and is now rapidly crossing the area of the solar system's scattered disk, making for the inner boundary of the hypothetical Oort cloud. It is not only the remotest man-made object in space, but also the fastest of them. All the spacecraft on their way to exit our system, being the first space probe to have traveled that far from the center of the solar system, Voyager 1 offered scientists a unique opportunity to study the heliopause. This is the area around our sun where solar wind pressure and interstellar gas pressure balance. When the charged particles emitted by the star collide with rarefied plasma, elaborate structures form out of elementary particles and magnetic fields. Studying them is crucial for understanding processes taking place in the universe. Unfortunately, by around the year 2025, the power of the radioisotope thermoelectric generators on board the probe will have run out completely, and the connection will have been lost. In 300 years, Voyager 1 is estimated to reach the inner boundary of the hypothetical Oort cloud. It will take the spacecraft approximately 30,000 years to go clean through, and after that, it will fly beyond the boundaries of the solar system. 10,000 years later still, the probe will fly by the star Gliese 445 at a distance of 1.6 light years, and then it will eventually get lost in the infinite depths. We can't help but mention its twin launched from the Earth on the 20th of August 1977. Voyager 2 had Saturn, Uranus, and Neptune for its targets, but it also approached Jupiter for a gravity boost. The images taken by this probe allowed scientists to assume that there are subsurface oceans on Ganymede and Europa. On reaching Saturn, Voyager 2 gauged the gas giant's temperature and magnetic field and discovered several new satellites. It goes without saying that lots of snapshots were taken of both Saturn's surface and its rings. Next in line on the probe's way were Uranus and Neptune. The flyby yielded a great number of unique snapshots, and in total, 17 of the two planets' satellites were discovered. Also, it was found that both Uranus and Neptune have ring systems. Under Neptune's gravitational influence, the spacecraft changed its trajectory and left the ecliptic plane. This meant that Voyager 2 wouldn't be able to approach the other objects in the solar system, but it still had other exciting things to look forward to. Thus, the probe was to collect invaluable data about interstellar plasma and cosmic wind, as well as to measure distances to stars and explore the heliosphere. The probe is currently as far as 128 astronomical units away from the center of our system, with a distance grabbing by 15.37 kilometers every second. It's going to take around 42,000 years to approach Ross 248, a dim red dwarf in the constellation Andromeda. The minimal distance between Voyager 2 and the star will be about 1.7 light years, and around 300,000 years since its launch. Chances are it will fly by Sirius at a distance of 4.3 light years. Unfortunately, it is impossible to distinguish such a tiny object from the Earth that far away. Of all planets in the solar system, Mars is the most suitable one for exploration. It regularly approaches our planet, with the distance between us becoming minimal, which is slightly under 56 million kilometers. Light and radio waves travel this far within a matter of 3 minutes. Needless to say, it takes spacecraft a considerably longer time. They have to follow complex trajectories around the system and perform gravity boost maneuvers when in close proximity to planets. On their way, the Perseverance Mars rover, for example, traveled to the red planet for slightly less than 7 months. The SpaceX Starship is expected to take considerably less to cover the same distance, but with exact data on this being gleaned, admittedly slowly, nothing definite can at this point be said about the duration of the planned expedition to Mars. Traveling to other stars is still more difficult. Even light, whose speed is known to equal slightly less than 300,000 kilometers per second, needs over 4 years to reach Proxima Centauri, the closest star to us outside our system. Incidentally, it would take the most advanced spaceship today to finish this same journey around 40,000 years. Come to that, even this figure is rather optimistic because there is the sun's gravitational influence to be reckoned with. A spacecraft will have to accelerate the speeds upwards of 47 kilometers per second, which will require incredibly large amounts of fuel, or else rather. Certainly, here's the revised text with proper punctuation. Time-consuming, although elaborately planned, gravity boost maneuvers on the way, unfortunately. Expectations of this kind of speed still border on fantasy. The fastest spacecraft today is the Parker Solar Probe, launched by NASA in 2018. Its speed reached as high as 147 kilometers per second in April 2021. In addition, after a number of upcoming gravity boosts planned for the nearest years, the probe will be capable of accelerating to a staggering 194 kilometers per second. In other words, approximately 700,000 kilometers per hour. Regrettably, the probe is moving to meet the sun rather than escape from it, and it cannot use the developed speed to exit our system. Most spacecraft, however, do not exceed a speed of a measly 11 kilometers per second. This is quite enough to send a spaceship into orbit or even reach the moon. As for getting as far as other objects in the solar system, a much more potent acceleration is called for. Unfortunately, even today's most powerful engines would not make for a fast flight. Speaking about interplanetary space probes exploring the outskirts of our system, it takes them decades to reach their destinations. The snag is that even the best modern rocket engines have a number of major drawbacks. The payload mass of the rocket's body accounts for just a few percent of its overall mass. The specific impulse, on the other hand, has reached its technological limit. If objects in the solar system can be reached by such rockets, at least in theory, traveling the stars definitely to boost the speed of a spaceship, with some of them appearing ridiculously incredible. Others are actively resorted to even now. To mention but one, ion thrusters, for example. By accelerating in an electrostatic field, charged particles give their impulses to the spacecraft. Even today, ion thrusters' performance shows to be 70 times higher than that of chemical-powered ones. This means that their use could not only boost spacecraft better but also allow their payload mass to be higher. Unfortunately, these thrusters are not powerful enough to take care of a spaceship lifted off from Earth. Yet, incidentally, they've been used since the 1970s on satellites and orbital stations for maneuvering and orbital adjustments. Another approach implies abandoning the idea of jet propulsion completely. Instead, The pressure of light can be used by capturing a stream of photons emitted by our sun. A solar sail is capable of boosting the speed of a spacecraft to hundreds of kilometers per second, and that almost without using any energy. Alternatively, solar wind may be captured instead of light. In this case, the sail is called an electric sail. Nevertheless, it is impossible to lift off the face of the Earth or any other planet by using this sail. Of course, other ways of producing a thrust may be used to enter space with a sail deployed later on, but this doesn't take care of the following problem. When a long distance away from any star, this engine is quite ineffective. The point is that the density of a stream of photons in interstellar space is much lower than in a star's environs. That is why it is quite hard for a spaceship like that to travel between stars. By the same token, the sail itself has to be made of materials that are both exceptionally tough and light. Probably graphene film or other scientific inventions will help develop these extra economical, although not very powerful spacecraft. Research in this field might produce a photon-powered starship. A powerful source of light could be created that would exert a force on a gigantic parabolic mirror, and a small amount of antimatter could create the necessary beam. This concept admittedly resembles something one could come across in science fiction. In today's stage of technological development, mankind isn't capable of designing either a mirror of this kind or a powerful enough source of light. Another way to produce thrust is to use the power of nuclear decay. As specified in a U.S. project dating back to the middle of last century, a spaceship equipped with a nuclear fusion-based impulse engine could reach Alpha Centauri in 130 years. Time. It would accelerate following a series of nuclear explosions around 1 kiloton each. The atomic shock wave would bounce off a solid thermal-resistant shield and easily hurl the spacecraft through and out of the Earth's atmosphere, boosting it to incredible speeds. The major drawback for going ahead with this kind of spacecraft was concerns about radioactive pollution of the launch site, as well as difficulties in producing an elaborate tablet. It is no easy matter to design a shield that would withstand a series of nuclear explosions. Even though not very powerful ones, in the end, the project on the construction of an impulse engine based on nuclear fusion was deemed to have no chance of success, and all research in the field was stopped. However, this doesn't mean that fission energy cannot be used for space travel. In the most elementary project of a nuclear engine, hydrogen is funneled through the active zone of a nuclear reactor, which is made of tough uranium rods. The heat emitted in the process of nuclear decay makes the gas reach high temperatures. After that, it is ejected from nozzles, thus propelling the spacecraft forward. This kind of engine is known as solid core, and excitingly, it is possible to construct one even in our current stage of technological development. Besides, the solid core nuclear thermal thruster's specific impulse is at least twice as high as that of today's chemical-powered ones. The temperature of the active zone of a solid core nuclear thermal rocket mustn't exceed 3,000 degrees Celsius on account of the destruction hazard of the construction elements. On increasing the temperature up to as high as around 25,000 degrees Celsius, the inner part of the reactor will crumple to turn into a cloud of red-hot radioactive magma. The efficiency of the engine, meanwhile, will be boosted dozens of times. This kind of engine is gas core. It may not only reach Mars as quickly as just in a few weeks' time, but may also break away from the sun's gravitational influence, and, in theory, radioactive plasma red-hot calls for complex technical solutions. Not a single kind of material is able to stop a plasma cloud as hot as tens of thousands of degrees Celsius. Early extremely powerful electromagnetic fields of specific configurations would be capable of that. Technology necessary to achieve this are being developed even at this moment. These technologies are also needed to develop a still more powerful engine, which would be powered by thermonuclear energy. Thermonuclear synthesis doesn't require heavy elements which are difficult to combine in space. Instead, hydrogen is used, the most widespread element in the universe. Besides, much more energy is released in the thermonuclear reaction than during decay of heavy elements. This type of thruster is estimated to be able to boost the spacecraft's speed up to 10,000 times more efficiently than the engines we have today, which means that getting to the closest stars may take far less time, just a few decades. The Bussard Ramjet is a hypothetical rocket project which is a modification of these fusion rockets. It is powered by a thermonuclear jet, and at its front, there is a huge RAM scoop. The ramjet is supposed to collect hydrogen in the interstellar medium and use it as fuel or working propellant fluid. When reaching a certain speed, the ramjet is supposed to collect as much gas as it uses to boost itself, making the Bussard Ramjet pretty much autonomous. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets like Crossed 128 bits or Gliese 667 cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of 3 components. 2 of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The 2 components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with a minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest, and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the radius of Alpha Centauri is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb Telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri b Ptolemy. It also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star. Its surface temperature is reportedly 5260 Kelvin, or slightly lower than 5000 degrees Celsius. With these factors combined, the celestial object has an orange hue, and its luminosity is, on average, twice as low as that of our Sun. Incidentally, Alpha Centauri b emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days, and whose radius was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first 2. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it the name Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its slow luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units, or 0.21 light-years, but in the next 300,000 years, it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts two confirmed exoplanets as well as at least one hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet, as the celestial body is extremely close to its host. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of many Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth if it does exist. If this isn't another measurement error, a year on this planet lasts about 5 Earth days and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether the space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now, but the 4.0 trillion kilometers of space vacuum between us are too overwhelming for us to cover. At this point, it takes light over 4 years to get there, but for humans, such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of the century. They will not measure sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by pulses of a highly powerful Earth-based laser. Estimates share that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. It's hardly a secret the distances in the universe are mind-boggling. Even with the best modern engines, a journey to the moon is going to take several weeks and more than 6 months to reach Mars by the most optimal trajectory. If we think about the legendary Voyagers, after 45 years of traveling through space, they managed to leave only the inner part of the solar system. They are destined to spend several of the next millennia drifting through the scattered disk and the hypothetical Oort cloud. The fastest spacecraft at the moment is the Parker Solar Probe, whose speed in 2025 will reach a record-breaking 194 kilometers per second. However, this will happen only due to the sun's gravity, which will never allow it to leave the environs of our star, and so the probe is doomed to soon burn up in its photosphere. Apparently, chemical jet engines, which are currently so widespread, have exhausted their development potential and are hardly suitable for interstellar travel. Of course, there are various alternative concepts, such as nuclear pulse propulsion or solar sails, but the implementation of either of these is hampered by a number of serious issues. It is highly likely that sooner or later most of these difficulties will be overcome. Another important task crucial for long-distance travel should be taken into account, namely the creation of a stable and powerful source of energy. All modern spacecraft are relatively small in size and are equipped with reliable but low-power power sources. For example, autonomous research probes are usually. Their power is consumed by life support systems, and the ion drives serve only to adjust the orbit. In the case of an extended manned mission to a remote planet or star, however, a spacecraft would need much more power. Meanwhile, 99% of the way to another star inevitably passes through interstellar space, devoid of obvious energy sources. Even radiation of the brightest stars is noticeably weaker here and dissipates in the vast expanses of space. Therefore, to travel to other worlds, we need an autonomous, powerful, and preferably inexhaustible source of energy. To figure out a potential way of solving this problem, we have to take a closer look at the universe's structure. It is there that a number of amazing physical processes can be observed, which might prove to contain a key to stars' secrets. To do this, we have to take a slight detour. In 2017, a collaborative effort of scientists from Princeton and Hong Kong yielded an incredible device that, at first glance, violates the fundamental laws of physics. A microscopic mechanism consisting of two silicon plates, spaced 100 nanometers apart, was able to generate a small amount of energy literally from nothing. It would seem that such a phenomenon should grossly violate the law of conservation of energy, one of the fundamental principles of the universe's makeup. However, in fact, it is not as simple as that. The amazing device is based on the Casimir-Poulder effect discovered back in the middle of the last century. Putting it simply, it boils down to this. If two thin plates are placed in a vacuum a very small distance apart, they will begin to be mutually attracted. The phenomenon is closely related to the Heisenberg's uncertainty principle, from which follows the existence of the so-called zero-point vacuum fluctuations. There are pairs of virtual particles that constantly appear at any point of the universe, by and large out of nowhere. However, their lifetime is only 10 to the power of minus 24 seconds, after which the particles disappear back into nothingness, and the global balance is restored. At the same time, if virtual particles with any parameters are generated in the open space, only those that have strictly defined wavelengths can be generated between the plates. Consequently, more numerous external particles press on the plates harder than internal ones. Just to illustrate, one can imagine that the space between the plates has a negative pressure. It's as if a little more substance were pumped out of the vacuum. The resulting mechanical tension can be transformed into an electric current, which is exactly what the Princeton and Hong Kong researchers did. And although the current was quite weak, it's the principle itself that matters, because this way, even a our world receives inexhaustible energy is of enormous practical value. For example, as an autonomous power supply for microprocessors and other high-precision equipment. For example, the Voyagers equipped with such a hypothetical battery could still transmit data from their instruments to Earth. This opens up promising vistas for exploring deep space. Many interesting physical phenomena follow from the Casimir effect, one of which is the so-called Scharnhorst effect. According to calculations, the speed of light in the space between the plates should exceed the standard value of 300,000 kilometers per second, because there are no collisions of photons with virtual particles. Although modern technology does not yet allow this experiment to be carried out, its mathematical justification leads to far-reaching conclusions. For example, the widely known project of the hypothetical superlunar engine, known as Alcubierre's bubble, was proven to be potentially feasible by scientists from Baylor University, Gerald Cleaver, and Richard Obusi. They combine the equations of quantum field theory and the general theory of relativity, producing a complex but clear rationale for a bold concept. It is worth mentioning that, according to quantum field theory, space has not three dimensions but many more, but this becomes noticeable only at the level of the microcosm. Applying the equations of this theory to calculate the Casimir effect, the researchers came to the conclusion that it is possible to control its properties with the help of a powerful energy impact. If we condense the space behind the hypothetical starship and make it more rarefied in front, then there appears an area similar to the Alcubierre bubble, which is capable of moving at superluminal speeds. The laws of relativity are not violated here because it is not the ship itself that is moving, but the space around it. On the other hand, from the very beginning, the main problem of creating such a bubble was considered to be the incredible amount of energy required. According to some calculations, an entire planet must be converted into radiation to form a sphere capable of accommodating a starship. If researchers manage to scale generators based on the Casimir effect to the required capacity, we will be able to obtain energy anywhere in the universe literally from nothing. Of course, there are still many problems to address for a starship to be fully operational because outer space is not the most friendly environment for humans. For example, it is permeated with deadly radiation, which not only destroys cells of living organisms but also causes negative mutations in their offspring. Thick metal shields or magnetic fields with certain parameters may be used as protection against it, and both of these approaches have their advantages and disadvantages. Another potential threat could be accidental collisions with micrometeorites and cosmic dust at high velocities. Even a tiny grain of sand has incredible kinetic energy and can pierce through a metal plate. It goes without saying that on a long interstellar flight, repair options are extremely limited, and a hole in the hull may prove to be fatal. In addition, a long expedition without support from Earth requires creating a closed biosphere within the starship. Scientists from different countries are currently working on this. For example, various plants have been grown on board the ISS for quite a number of years, both for scientific purposes and for consumption. In addition to that, engineers are developing systems for recycling waste, including biological waste products. However, a fully fledged orbital ecosystem is still a long way off. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from Earth. Some of them are single stars, while others contain two components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs as we slowly recede from our home planet. We will cover dozens of light-years of space and visit quite a few remote worlds. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation JG699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years, but the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 31-34 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, It isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of Earth. The planet, named JJ 699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives. The surface temperature of the celestial body is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. Among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. So afterward, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at a time was destroyed by this explosion. Its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits. 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever, leaving the vicinity of Sirius permeated by lethal ultraviolet radiation and stellar wind. We will perform a maneuver near the solar system to reach a small star 14 light-years from Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3272 Kelvin, or about 3000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system nearest. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first, our closest exoplanet to the parent star, is called Wolf 1061 bits. It is located 0.38 astronomical units from the center of the system and completes the full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. And the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanets completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its equilibrium temperature is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, even variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher and conditions on the planet could approach favorable. Of all the potentially habitable exoplanets known to date, Wolf 1061 is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit with a distance between the parent star and the aphelion reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061 is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. On the other hand, this planet falls into the category of mini Neptunes with a thick, multi-layer atmosphere. Its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061 never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of the top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived on Earth from no other place other than the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Column, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long. Here is the revised text with proper punctuation. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Column contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Column is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf, Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370 bits. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370 bits is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an even distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which, combined with an abundance of liquid water, may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis, and Gliese 370 bits was considered one of the most favorable exoplanets for potential biologic life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370 bits remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light, as the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general. Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2. Be verified at this point. Although the stars were visited are great distances apart, they're all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It has a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the cellular system's motion is the so-called bubble one, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. Throughout history, people have been motivated by curiosity and inventiveness. It is thanks to these qualities that the available technologies today get actively upgraded. What used to seem like science fiction just a measly couple of decades or so ago is now successfully becoming part of our lives. We're launching great numbers of satellites, building gigantic observatories, and constructing orbital telescopes to find out yet more new things about the world around us. Perhaps it is thanks to all this that humans will reach distant stars someday after all.